We're good? Okay. So this is a lecture about action potentials. It's going to be about the creation of the impulse and the transmission of the impulse. Okay. So I'm going to draw some stuff. We're going to start by looking at the axon. So you can imagine back here is, the cell body and the dendrites, but I'm just showing you the axon of this first neuron right now. And axons end at an expanded area called the axon bulb, right? So there's going to be some part of what we talk about right now that will be familiar because we talked about synapses, right? When we did neuromuscular junctions. And so some of this will be familiar, and then we're going to kind of expand on that concept. Okay, so this is, we're going to call this our presynaptic, that just means before the synapse, presynaptic neuron. Okay, and then axons, generally, when they are communicating with another neuron, most of the time, they communicate with the dendrites of another neuron. Because remember, axons carry impulses away from the cell body, and then dendrites receive information. They are input extensions off the neuron. Now, there are other types of synapses. You can actually have an axon synapse with the axon of another neuron. You can have synapses between axons and cell bodies of another neuron. There's all different types of synapses going on in your body. But the most common one is between the axon of one and the dendrite of another, so that's what we're gonna do. So what I'm gonna draw here is representing the dendrite of the postsynaptic neuron, the one that comes after. So I'm just gonna kind of go like this, and I'm gonna call this the dendrite, and this is gonna be our postsynaptic neuron. Okay, how's everyone feel about this? Everyone's good with this? Okay. If I were to draw a dotted line around the synapse, just to clarify what that word means. Synapse, by definition, is just the functional connections between two communicating cells. That's what it is. So it involves the end of one cell, the end of the other one that's being communicated with, and the space in between. So I could sort of do a line like this, and that would sort of represent generally the synapse, the connection. All right, the space, what's the space called?
Synaptic cleft.
Very good. This is the synaptic cleft. Okay, awesome. So we know that impulses, electrical messages, travel down the axon, and we call those impulses action potentials. Now, I'm going to explain how they're created, but we're first going to look at how it crosses the synapse, and then we'll look at how it's created in this second cell, okay? All right, so the action potential or message is traveling down the axon, and when it gets to, let me get my, when it gets to the end of the axon, it causes something important to happen. And that is, it causes these channels to open in the axon bulb. And these are calcium channels. And so when calcium channels open, calcium comes in to the axon bulb, calcium ions. And you may be asking, well, where do they come from? They live out here in the extracellular environment. The environment outside of your cells is an aqueous environment, it's a liquid environment, and it contains all kinds of ions. Sodium, potassium, chloride ion, calcium, it's got a ton of ions. So calcium lives out here. And when these specific channels open, they are drawn from out here, where there's more of them, to in here where there's less of them. Okay, so calcium comes into here, and the reason that happens and is important is because there are these vesicles that exist in the axon bulb. And we talked about these, right? These are called synaptic vesicles, and they're filled with chemicals. Now, the type of chemical, it just depends on the synapse. Now, when we did neuromuscular junctions, that chemical was acetylcholine, right? And that could be the chemical in our example right here. If these are neurons communicating in our brain or spinal cord, it could be acetylcholine. But it could be dopamine, it could be serotonin, it could be norepinephrine, it could be a lot of different things. So we're gonna keep it general right now and just say neurotransmitter, okay? And the reason that the calcium coming in is important is because it makes these vesicles excited, it makes them move to the very end of the axon bulb. So you could kind of draw a little arrow like that. And it makes them fuse with the end of the axon bulb and then release through exocytosis that cargo it's carrying, the neurotransmitter, out into this space. So without that influx of calcium, that wouldn't happen. And the calcium is coming in because channels are opening in response to the action potential. Everybody with me so far?
Yes.
Awesome. Okay, so we have this neurotransmitter, whatever it may be, released into the synaptic cleft. Now, in the membrane of the postsynaptic neuron, there are receptors. And again, this is, I know, familiar, but it's worth reviewing. And these receptors are gonna be specific for this neurotransmitter. In fact, neurons connect to each other based on the receptor of one matching up with the neurotransmitter produced by the other one. Okay, it's a very specific type of junction or union, I should say. So what happens is, the neurotransmitter chemicals are gonna bond, usually a couple to each receptor, like that. Now there are a few different mechanisms that neurotransmitters can do. Sometimes they bond to different things. This is the most common scenario, so this is the one we're gonna look at. And when that neurotransmitter bonds to the receptor, it opens up. Bless you.
Yes, yes.
And it becomes an ion channel, right? And if this synapse is what we deem a stimulatory synapse, meaning I want this action potential to be recreated here and then go down that next neuron, that's called a stimulatory situation, then these channels are likely going to be sodium channels, okay? We'll look at an inhibitory situation later, but right now we're gonna look at a stimulatory situation. So, sodium channels, this receptor becomes a sodium channel. And just like we had calcium out here, we have a ton of sodium. Sodium is the #1 extracellular ion, meaning of all the ions in your fluid outside of your cells, it is the highest represented ion. There's a ton of it, okay? All right, so here's what happens. Sodium moves from the extracellular environment into this cell through these channels that have opened because the neurotransmitter bonded to it. And so we have this influx of positivity. Would you agree? Okay, so let's look at this cell for a minute. Of course, of all the days, I didn't bring my water. I'm feeling very thirsty. Okay, so let's look at this cell for a minute before we move on. Whenever an excited cell, meaning a cell that's capable of being innervated by a nerve and responding to that nerve, that's an excitable cell. Excitable cells are muscle cells, are neurons, even glandular cells are excitable because they can be innervated by a neuron and then secrete something. Any excitable cell has what's called a resting state. when it's not being contacted and it's just basically sitting there doing nothing, okay? And that's called, its resting state is called its resting membrane potential. Because its resting state basically is an electrical charge that indicates it's not doing anything. And for neurons, that value is minus 70 millivolts. So that means if I took a little probe that detected a charge and I put it to this neuron, to the outside of it, and it wasn't receiving any stimulation, it would be sitting at minus 70 millivolts. Okay, so let's assume that's where this one was sitting at minus 70. But now, all this sodium is coming in. So what is that doing to its resting state?
Agitating. It's kind of agitating.
It's agitating and it's becoming more positive, right? So if I'm sitting at minus 70 and all of a sudden these positive ions come rushing in, then this number is going to change. And maybe it's going to change and become minus 67. Maybe that's, with the first influx of sodium, it goes to minus 67. We call that change an EPSP. This stands for excitatory postsynaptic potential. It's not an action potential, it's just an excitatory postsynaptic potential. We've changed a little bit from our resting state to a slightly more positive number, okay? An excitatory postsynaptic potential, generically, that's called a graded potential, not an action potential. It's temporary, and it will only be maintained if more sodium keeps coming in. If this only happened once, and sodium came in one time, and we went from minus 70 to minus 67, and no more sodium came in, it would gradually go back to minus 70. Okay, it wouldn't be permanent, because the sodium would eventually diffuse out, and we would return back to a resting state. What determines how much sodium comes in is back here. And it's not the strength of this action potential, because as you will see later, all action potentials have the same amplitude or strength, okay? It's the frequency of this action potential coming down, because neurons don't fire once, they're gonna fire multiple times. So if this presynaptic cell, let's say an action potential is coming down at this rate, kind of slow, right? That can cause sodium to come in, but it might not cause enough to come in to get to where we need to be, which I'll get to that in a minute. But if the action potentials are coming down this cell like this, you're gonna have a lot more sodium come in, okay? All right, so that is what determines how much sodium comes in. The frequency of this action potential, not the amplitude. It's the frequency, how many. Okay, so the more that come in from here, more action potentials, the more sodium. And we keep having sodium come in, and we keep getting more positive. So this change, we said, that's called an excitatory postsynaptic potential. And we have a word to describe what it means when a cell is becoming more positive. We say that the cell is depolarizing. So excitatory postsynaptic potentials are depolarizing potentials. Depolarizing, again, just means becoming more positive. So these graded potentials in our example are depolarizing the second cell, which means making making it more positive. That's what depolarizing means. So as more and more sodium comes in, we could see this going to minus 65. Maybe it goes to minus 61. All of these are EPSPs, they're depolarizing stimuli, and we're getting more and more positive. Everybody with me?
Yes.
Okay. There is a magic number we want to hit, okay? We can't just depolarize a second cell, we have to depolarize it to this magic number. And that magic number is called the threshold for this second cell. And for a neuron, it's minus 55. That's what we have to get to. We have to have enough sodium come in that this cell goes all the way from minus 70 to minus 55. And you can imagine, as more and more sodium comes in, it's packing and filling the dendrite, it's moving toward the cell body, right? And the cell is just getting more and more full with sodium, correct? Right? It's moving through the cell and getting to the cell body. And eventually, if enough sodium comes in, and it comes in quick enough before it can diffuse out, and we hit that minus 55, we're gonna see recreation of this. And that's what I'm gonna show you next, all right? All right, so I'm gonna erase this so I can draw some more stuff. Y'all wanna take a pic, and then. You good? Okay. Okay. So now what I'm gonna do is I'm gonna draw the, we're still, now we're looking at the postsynaptic cell. We know that sodium's been coming in, we know that, right? So now let's say we're at the cell body of the postsynaptic cell, like I said. And this thing is just filling up with sodium. We've been having all these graded potentials, these excitatory potentials. We're getting closer and closer to minus 55. Let's say now that we hit minus 55. That's called the threshold. Here's what's gonna happen. The action potential from the first cell is gonna be created now in this cell. And the point of creation is at the axon hillock, that initial region of the axon, because action potentials are axonal events. All the previous potentials that were created getting us to the action potential, those graded potentials, those are not axonal. They're not happening along the axon, they're happening at other areas of the cell. But now we've reached the axon hillock, which is roughly like this area right here, the beginning of the axon, okay? And so there is a little bit of there's an anatomical change at the axon hillock as far as the channels that are located there. Everywhere else, there's sodium channels that are opening and letting sodium come in, down at the beginning where we look. But now when we hit this magic number, there's gonna be a massive opening of sodium channels right here at the axon hillock. And it's this phenomenon called voltage regulation, where the sodium channels at the axon hillock, they recruit other sodium channels. So as soon as one is stimulated to open, exponentially more will open, because it'll be like, hey, I just opened, you wanna open, you wanna open, you wanna open? Like they recruit others to open, almost like a positive feedback situation. It's called voltage regulation, Okay, so you get this massive influx at the, and I'm just gonna stick with pink because you know that means sodium. You get this massive influx at the axon hillock. It's so massive that, and it only starts to happen when the charge of this neuron reaches minus 55. But there's so much gonna come in that we're gonna actually overshoot this and go way beyond it at the point of the axon. In fact, we're gonna go all the way to positive 30. That's generally how much the charge changes. And it's just because of the massive amount of sodium that comes in. And once we get that change and it goes all the way to positive 30, here's what's gonna happen. These channels are going to close all of a sudden in this area. And what's gonna happen is different channels are gonna open. And those channels are potassium channels. When potassium channels open, potassium doesn't come in to a cell, it goes out. Because remember I said sodium is the #1 ion outside of your cells? So if you open channels, it wants to rush in from high to low. Well, potassium is the #1 ion inside your cells. So if channels open, potassium's like, let me out, and it flies out. So right after you have this massive influx of sodium through voltage regulation, and we get all the way to positive 30, they slam shut, followed by opening of potassium channels. And potassium rushes out. So now you're losing positive ions, right? That means you have to be going back the other way, becoming more negative, right? So we just had this massive change here, all the way to positive 30. And then what's gonna happen is right here, it's gonna go all the way back to minus 70, right here. That is called repolarization. It's repolarizing back to the beginning. And then all of that sequence keeps happening all the way down the axon. You get this massive opening of sodium, it rushes out, okay? And we go to positive 30, rushes in, we go to positive 30, slam shut, and then potassium channels open, it rushes out, we go back to minus 70. And then it goes back and forth all the way. That's what an action potential is. If you read the definition of an action potential, it says it is the rapid change in the resting membrane potential of a neuron. That's the definition. And so what you realize is the action potentials, more than being electrical, are really chemical. They involve ions moving in and then moving out, moving in, moving out, moving in, moving out. That is what an action potential is. And that ionic movement alters the resting membrane potential from being very negative to being very positive, and then going back to negative and positive. And that return that keeps happening makes sure that the action potential keeps moving forward and doesn't go back the other way, okay? But once it's created here, this opening and closing scenario is going to happen all the way down the length of the axon. And there are 3 important qualities of these action potentials. One is that they are irreversible. So once they start going this way, they're never gonna go backwards, because of the alternating nature of the sodium and potassium channels. They are also conducted without decrement. That means that the action potential at the axon hillock is exactly the same strength as it is at the axon bulb. It doesn't like get lighter as it goes down or lose its amplitude or strength. It's exactly the same here as it will be at the axon bulb. And then the other quality is called the all or none law. And that means once it's created, it's going all the way to the end. It's not gonna peter out halfway down or die out or stop. It will go all the way to the next synapse and make something out, and then it will happen again. Those are the 3 important qualities. And those are different from the graded potentials we saw earlier. because those graded EPSPs, they are not all or none. They don't adhere to those qualities, because if you only had a few EPSPs and not enough to reach minus 55, the neuron would go back to minus 70 naturally. It's kind of like, think about dropping, this is an analogy they do a lot in textbooks. When you drop a rock into like water, right? If you dropped a little pebble into water, it would like make a wave, right? That would go out like this. But it wouldn't keep going forever, would it? No, it would eventually dissipate, right? And disappear. That's how EPSPs are. Now I can try to get more out of my EPSPs if I sum them, I add them together, and I keep dropping. Imagine if I keep dropping a pebble in the water. Ding, ding, ding. The little waves are gonna get a little bit bigger, right? And they're gonna be consistent as long as the pebble is being dropped in the water. And you may, if you get a big enough pebble or big enough rocks, you may have a little wave form, right? That would be like an action potential. But as soon as you stop, those little waves go away. And that's like graded potentials. I can add the graded potentials together. I can maximize their effect, but they are not all or none like action potentials. All right, let me explain now the effect of myelin on this process, because we talked about how a lot of axons have this myelin, right? This fatty sheath around them. What were these spaces in between called? Yeah, very good. Node of Ranvier. And what did we say that myelin does as far as the action potential is concerned? What does having myelin along the length of an axon, how does that influence the action potential? It speeds it up. Doesn't make it stronger, it makes it faster. Okay, and here's why. When you have myelin around an axon, it's like putting a jacket on the axon. It's like wrapping it in an insulating material, right? And that means that in the areas where you have the myelin, there are no sodium and potassium channels. Okay, they can't exist when there's myelin wrapped all around. So the only place you have the functioning sodium and potassium channels are at the nodes, okay? So when you have an action potential created at the axon hillock of a myelinated axon, you're gonna create it here, and then it's gonna be created, and then it's gonna kind of jump to here, and then we're gonna recreate it right here at this node, where sodium and potassium can go in and out, okay? And then it's gonna be recreated here at this node, where we can go in and out. It's going to have this sort of appearance that the impulse is jumping from node to node. That's called saltatory conduction. And that's pretty fast, because you get to skip whole regions of the axon, right? Whereas if you have an unmyelinated axon, no myelin, you have to create the action potential at every point along the axon, not just at the nodes. And that takes longer. That means the impulse is going to take a lot longer. Here's the analogy they'll use, and this is a good one, I think. If you're at a football game and you know how the wave gets initiated around the stadium, and everyone goes, stand up, sit down, and then your neighbor, stand up, sit down, and your neighbor, stand up, sit down. So once you stand up and sit down, which by the way represents opening of sodium channels, closing of sodium channels, opening of potassium. Okay, that's what the standing up and sitting down means. If you have to do that with every person, and you've probably all experienced that maybe, or at least seen one, it takes a while for the wave to get back to you, right? You might be sitting down for a whole minute before it actually reaches you again. Or maybe 30 seconds, 45 seconds. But imagine if the wave was only every like 100th person had to stand up and sit down to make the wave go around. Do you see how that would be a lot faster? not every single person standing up and sitting down, but I stand up, I'm in seat 100, and then the guy in seat 200 stands up, and then the guy in 300 and 400, and that gets the wave back to me a lot more rapidly. When we conduct down an unmyelinated axon, this is called continuous conduction. It's slower, and this is called saltatory conduction, and it's a lot faster. And then once the action potential gets down to the axon bow of this cell, the same thing happens with whatever cell it's contacting next. All right? So that is what an action potential is. There's some key things just to reiterate. It's an axonal event. There are no action potentials happening at dendrites or cell bodies. An action potential is only created once we hit -55 and the axon hillock initiates the action potential. Okay, we do have an overshooting of that threshold because of the voltage regulated sodium channels that open and we get such a huge influx. And the reason for that overshoot to +30 helps make sure that the action potential doesn't back up and try to go back the other way. It keeps it moving forward. Once you create an action potential in a region of the axon, it can't move to the next region until that region repolarizes back to -70. And then it goes to the next region. And then it goes all the way to -55 / +30. And then it goes back to -70, and then it moves to the next one. And then remember the three characteristics. Action potentials are irreversible. They are
non-decremental,
conducted without decrement, and they adhere to the all or none law. The last thing I want to say is, so we've been looking at a stimulatory situation, right? We've been looking at when the presynaptic neuron releases a neurotransmitter that attaches to receptors that leads to the opening of sodium channels, causing depolarization of the second cell. But you can have inhibitory synapses, where one cell contacts another cell in an effort to make this cell not fire an action potential. That's called an inhibitory situation. When that happens, let me erase this so I can, I did that, okay. Show you like what might happen with an inhibitory situation. And I'll give you an example of when an inhibitory situation exists. Yeah. Okay. So obviously when we learn this, we mostly focus on stimulatory situation, but you may have a scenario where you want to inhibit. When that happens, so you have the axon will release neurotransmitter into the cleft. The dendrite of our second cell, our receptors, and we bind to the receptor. All that's the same. But if this neurotransmitter at this particular junction is an inhibitory neurotransmitter, here's an example of what could happen. These might open up and become channels, but instead of being sodium channels, maybe they're chloride channels. Chloride ion is a negative ion. So maybe they're ions where you see an influx of negative ions like that. And so this cell was sitting at -70, right? It was just minding its own business, not doing anything. And now it goes to -73. And then maybe more chloride comes in, because this one's firing. And it goes to -76, and it goes to -80. Okay, this situation, these are IPSPs. These are inhibitory postsynaptic potentials. And what inhibitory postsynaptic potentials do is they do something called, they hyperpolarize the second cell. And that means they make it more negative. Well, if I make the second cell more negative, it's getting further and further away from that minus 55 magic number, right? So this cell, we could say, is very unlikely to generate an action potential because it's being inhibited. It's being hyperpolarized. It's what's being created are IPSPs. That's called hyperpolarization. So again, as long as this is firing, this hyperpolarization will continue, but as soon as it stops, eventually these will diffuse out and we'll go back to minus 70. But the point of this is to make this not fire. Does that make sense?
Yeah. It's just in what situation that would.
Let me give you an example. So here's a great example of that. So have y'all heard of the hormone melatonin? Okay, what do you think of when you think of melatonin?
Sleep.
Sleep, right? So melatonin is released from a gland in your brain called the pineal gland. And it surges at night, right? It starts to kind of increase its amount as the sun goes down, 6, 7, depending on daylight savings time. And it's really kind of at its peak at, say, between midnight and 3 o'clock in the morning. And that helps you stay asleep. That's why we take supplements of melatonin to try to help us sleep, right? So I just gave you a time frame. So it starts to increase in the evening. It kind of hits its peak in the middle of the night when you're sleeping. And then the melatonin levels will go down. It's a negative feedback loop. Okay, so it's peaking when you are at the height of your sleep. Would you want melatonin being released from your brain during the day? No, that would not be good, right? So here's an inhibitory synapse that exists. This is really cool, actually. You have cells in your retina of your eye that are sensitive to natural light from the sun. And you don't have to be out there, just it coming in the windows right now, okay? And that sun hitting your retina, there are cells that send a signal to your pineal gland from your retina that inhibit the pineal gland during the day. And make it like, hey, hyperpolarize the hell out of it so it doesn't release melatonin. And then the sun goes down and that stops. And so as soon as that retinal influence, that inhibitory influence on the pineal gland starts to diminish, the pineal gland's like, all right, I'm gonna start making melatonin, right? So that's an example. There are other inhibitory synapses. One of the things that was asked in your lab was talking about tetanus, right? Tetanus interferes with inhibition that happens all the time. When you go to do an action, let's say I go to, grab that camera or whatever, I'm engaging muscles like flexing my elbow, flexing my shoulder, extending my elbow, extending my wrist. Mm-hmm. At the same time I'm doing that, the opposite muscles are being inhibited. Because if when I went to flex my shoulder extensors were also contracting, I'd be in spasm, right? So I need to inhibit contradictory antagonistic muscles when I do an action that I want, an agonistic action with agonistic muscles. I want to relax or inhibit the antagonist, and that's a reflex that happens. So there's all kinds of inhibition that goes on that helps you live a comfortable existence in your body. But those are two that I just thought of to share. Any questions? You can stop. Thank you. Bye.